Okay, so hey everyone, welcome to week 3 of the applications of AI. And this week we're going to talk about AI with medical images. So I'm Kevin. I'm one of the people on the AIMS team, and I'm VP External. And this presentation was edited by my friend Zoni. So I guess let's jump into it. So first, what we're going to talk about is we're first going to talk about the data. So data is very important part of the machine learning for any machine learning project. And especially for medical imaging, there's a lot of extra considerations that need to be thought about. And yeah, next we're going to talk a little bit about the tools and machine learning models. And finally, I'm going to go over 3 examples of applications of AI in medical imaging. So let's start off with the data. So what exactly does medical image data look like? So medical image data can be basically anything from medical equipment. So from an MRI machine, you get MRI scans. From X-rays, we have ultrasounds. All of these count as medical imaging. Not just that, there are many other types of medical imaging, such as fundus photos, which is when you take a little camera and you take a picture of the retina or the eyeball through the pupil. And there's many more, such as this skin cancer image. Yeah. So now that we know like what medical imaging looks like, we'll get into why is it important. So in fact, most of the time for machine learning projects, it's actually spent on data curation or processing the data, getting the data, all things like that, getting ethics approval. In fact, I believe there was a paper that came out and that said like for most projects, it's like 80% of the time is spent on data curation and 20% is on like model development. So data is expensive, especially medical imaging data. I think it can get up to like tens of thousands, hundreds of thousands for like some projects, just data alone. And the reason for that is that the data needs to be high quality. So what I mean by that is that there's no artifacts, the images are good resolution, there's no motion blur, stuff like that. There's some nuance to that, which I'll come back later, because as you know, machine learning models need to be generalizable, and having data that is extremely high quality, is not something that you actually see in a clinical setting. So if you train your model on, all high quality data, it's not going to be generalizable to, maybe lower quality data in like in the field, right? So the next thing is that we need a large quantity of data. So with ML models, you know that with backpropagation, you need to do a lot of iterations. You need a lot of data for even a small model. And there's no set, a specific amount of images, like 100 images is good enough or 1,000 images is good enough. It definitely varies depending on the project, right? So if you're looking at maybe a task that is fairly easy, like locating where the liver is, or detecting if the patient has a liver, that might be a very easy problem where you wouldn't need that much image. But if you're trying to diagnose or predict a much rarer disease, you would need more techniques or more data. Another thing is that often the data is rare. So like I said before, like some of these rare diseases, there's not that many pictures or medical images that exist, right? Just because there's not that many patients with that disorder. So you would have to either use a lot of techniques like data augmentation to make do with what you have, or collect more in the field. That could take much more money and much more time. We also need data that is labeled. So what I mean by that is that it either has to, it depends on the task that you're looking for. So if you want to predict a disorder, you would need images that have a label of this patient has the disease or this patient is healthy, or the controls, right? And sometimes this is quite difficult to get because for some disorders, like there's disagreement among physicians. Like some physicians might think this patient is diseased, or some physicians might refute that. So getting a proper label or the ground truth is sometimes quite difficult, and all of these factors make it so um, image medical imaging data is quite expensive. Another problem is that medical data is, or imaging data is quite messy. So artifacts, even though these like MRI machines and these expensive equipment are quite like high level, there's always going to be some artifacts. So examples would be, motion artifacts or just equipment malfunction. And, including these things into your data might negatively influence the model training. And it's up to the researcher or the physicians to be able to, do a quality control and take these out. And, that can get quite laborious, labor intensive. Another thing is that there are equipment differences. So each MRI machine or each different medical equipment has their own basically signature. So between each equipment, the data is going to look slightly different. And you want to make sure that your model when training does not pick up on that, because it might be able to predict, all these patients come from this region when in fact it's just picking up on, um, you know, patterns that the machine created into the images while I was making the images. Another thing is that, well, these next 2 points kind of tie in together. So small sample and not generalizable. So if you are a physician that is looking to create data for an ML project, you would probably collect data in your one hospital or your one clinic. And this might mean that the population that you're getting is not too diverse, right? Because they all live in the same area. And this can also extend to populations or samples with the same age, same sex, or same ethnicity. And this might not be able to generalize to different clinical settings if you want to implement your model somewhere. So being conscious of having a very diverse sample is quite important when you're getting the data for this. Another thing is ground truths. So like I said before, it's quite difficult to know exactly what is the ground truth. Sometimes something like a biopsy will confirm when diagnosis is not too clear. But again, this takes time and it's not always available. Ground truths also require experts. So if you were a machine learning engineer, you would have to hire some experts like ophthalmologists to label the data for you, which can get quite expensive. Another option is crowdsourcing. So you can get a lot of physicians to basically decide on what would be the best label or best segmentation of the image. And both methods are quite common. And lastly is ethics, right? So medical data is patient data, and obviously you want to be able to protect a patient. If you publish a work with this type of data, you don't want someone to find it on the internet and trace it back to the patient, right? Yeah, so patient confidentiality, and I'll go on a little bit more about this. Yeah, so like I said before, patient data needs to be protected. We don't want, once a project is published, we don't want anyone to be able to trace it back to the patient. So we want to remove some of that information from the images. So all we really have to work with is the images. So two terms I like to talk about is anonymization and de-identification. So with anonymization, what that is that we completely remove all identifying markers of an image. So for example, chest x-ray, we would remove anything that could lead us back to the patient permanently, right? So we only have the image to work with, and that's what we'll give to the ML technician. Comparatively, de-identification is where we don't necessarily delete that information, but we obscure it. So we have a list somewhere, maybe in a secure server, that says, this is patient one, which has been redacted when we're working with, and we can get that information if we choose to need it. And this is important for follow-ups, right? If we're wondering how has this disease progressed, did this patient actually have the disease after like 1 year, we could submit another ethics proposal and take a look, recover that ID, and take a check it out, right? So again, just to recap, anonymization is permanent removal of the markers, while de-identification is just more or less covering it and obscuring it. Obviously, anonymization is more safe for the patient, but in cases where you need it, the identification is a useful thing to implement. So the next thing I'd like to talk about is prospective versus retrospective. So this is more in line with the type of study. So prospective would be, you have your research question. So let's say you want to be able to detect cancer in medical imaging photos. In a prospective research question, that's all you have, right? You have your research question and maybe you have some other preparation, but you don't have the data yet. So what you would do is that you would submit an ethics proposal for the data and you would go collect it. And prospective research is more, it's more expensive because you have to collect the data yourself. It takes more time and it requires, an ethics proposal. So you would ask, like, why would anyone choose to do prospective versus retrospective, where you already have the data? Well, prospective allows you to basically choose your patients, right? Allows you to have a data set that is much higher quality because you get to pick who's included in your data set, you get to pick what you measure, you get to pick the image quality. So you basically just get exactly what you're looking for in exchange for more time, more money dedicated to the project. Retrospective, however, is that the data is out there somewhere, right? So somewhere on the internet or somewhere in a secure database, there is a lot of medical images with cancer imaging, and you will be able to access this, maybe buy it, and you will be able to work with it. And this is much quicker, less expensive. You do not need, with some exceptions, ethics proposal because the data is already on there. But however, you kind of have, you get what you get, right? All the data is already there. The only data you can work with is on that database. You can't get more data. So you're kind of limited with image quality, right? So it's kind of a trade-off on what kind of project you want to do. Often you can employ a mix. So there is a database and you want to add to it to maybe get more high quality data. And so maybe a mix. So for ethics proposals, this usually takes a long time. So you would need like an initial ethics proposal for being able to work with this patient data, how you would make sure that it's confidential, how you could make sure that it's safe on this project. And often researchers would want additional information like clinical data, maybe the age of the patient or the gender of the patient is important for this diagnosis, and they would have to continuously submit these ethics proposals if they have to change their project, right? So it was very time consuming, and this can take months to years. The next thing I'd like to talk about is PACS. So this is picture archiving and communication systems. So this is a tool used by physicians where the data that they get is stored in a non-physical secure server, right? So this kind of centralizes a lot of the patient data, and only physicians are able to access it, not ML technicians. Because of this, clinicians or physicians have to work together with ML engineers to basically get access to it and work on it. The next thing I'd like to talk about is synthetic data. I get a little bit more in depth on this one, but synthetic data is generated basically using other machine learning models where they make basically fake patients based on real patient data. And because these aren't real patients, you can basically do a lot more with them without ethics approvals. So it's a lot cheaper. And for projects that you need a lot of data, this is a pretty good alternative. Another thing that to be aware of is what we call quasi-identifiers. So even if we remove all the dates, all the names, all the the information from a image, if the image depicts a statistically rare disorder that maybe only like a few people in the world have, it doesn't really matter if you remove all that information, right? Like seeing that picture, you can trace it back to that patient. So this is something to be made aware of, and you need to be conscious of it. And HIPAA guidelines, basically, I think there's like 18 things that you have to remove from an image to de-identify it. And I think that's on the next slide. Yeah. So names, zip code, telephone numbers, patient ID, stuff like that. And it's quite strict. So yeah, some things to be aware of. If you're working with clinical data, you have to be quite conscious of not accidentally revealing anything about patients. All right, so that was the data portion. Now we'll move on to something more exciting. So why machine learning? So how machine learning can help medical imaging and disease diagnosing through medical imaging is that often there is a shortage of experts. So for one of the examples that I'll be talking about later, for diabetic retinopathy, it's a disorder that's easily treatable, but in some places there's not enough ophthalmologists, right? And this can be quite a big problem because non-treated, it could lead to blindness. So being able to have this quick model or algorithm that can diagnose it, could prevent this, and that's kind of the rationale behind their paper. Another thing is that there is a lack of precise diagnosis. So more diagnoses. For some disorders, physicians aren't really too sure about the diagnosis. They can be split on it. Some might think it's quite severe, while others might think it's not too bad, judging from the images. And having a Bayesian approach using machine learning might be more rigorous in doing so. One problem a lot of people ask is that if the physicians and experts can't diagnose it from the images, how can the machine learning model do it, right? Because if you have labels that are not 100% confident, how can you do that? So in that case, that kind of falls in line with the ground truth, right? We don't really know what the exact ground truth is all the time. And there are ways around it. So like maybe a physician is not too sure about the diagnosis from the image alone, but they do a biopsy, which confirms it. In that case, we would get the actual ground truth. So that would generate a label for the machine learning model. Right. In other cases, there could be quite complex problems. So a lot of data, a lot of features, clinical data, 3D modeling, and stuff like that. That's kind of a strong point of machine learning. It gathers a lot of different features together. Another thing is that it is fast and automatic. So and it helps with work list prioritization. So what I mean by that is that it can act as more or less an early warning system. So for a physician, where they could scan through the image and say, oh, this patient has something interesting on their chart or something interesting on their imaging files, right? And to alert the clinician, not really diagnosing, but more or less kind of just alerting them to it, to tell them which patients they should focus on more. Also, some disorders have invasive diagnosis. So maybe like the biopsy example I said earlier, where you can accurately diagnose a disease using a biopsy. However, that is invasive. It poses a risk to the patient. And so finding an alternative diagnosis method through machine learning through imaging, which is less invasive, is something that is needed. Okay, so then we'll get into what are some things that AI can do, and this is more in line with medical imaging, or just imaging in general. So the first thing would be prediction. So this would be could either be binary. So does this patient have cancer or not, or multi-class? Maybe how severe is the cancer? What stage is it in? Next, we have segmentation. So localization would be just detecting where in the general vicinity an object is, or like maybe a tumor is. Segmentation, semantic segmentation would be telling you which pixels on the screen or on the image are part of that class, and instance is for multiple instances. Something that is quite interesting for medical imaging is reconstruction. So reconstruction is where we take noisy frequent signal data. So like PET scan, yeah, PET scans, the raw data is a sinogram, and for PET scans that are lower quality or not as high quality, machine learning models can basically take that sinogram data and transfer it into a good looking PET scan image. Another thing is that synthetic data. So this uses GANs, or generalized adversarial networks. Basically, it trains two models to create patient data that is as realistic as possible, so that we can't really tell the fake patients or fake patient data from the real patient data. So these are some examples of what you could do with machine learning in medical images. Next, we'll talk about kind of the bread and butter for medical imaging when it comes to deep learning, which is CNNs. So CNNs is short for convolutionary neural networks. And this kind of builds on the typical neural networks where we have a bunch of nodes feed into more nodes or neurons. But instead, for each this one uses, or CNNs use what we call kernels. So these sliding kernels basically go across the image. So in this image here, we have approximately what a CNN looks like. When we take the input data, we use these sliding kernels, which look like these. I believe this one, when we slide it across the image, we create a feature map. So depending on what kind of kernel it is, we'll get a different feature map. So the kernel here is for edge detection. So if we scan through this kernel through our image, we'll find the edges on the feature map. And as we go deeper and deeper, or the shallower layers on the CNN represent more basic features, so like edges or color blobs. And as we get deeper in the layer, we get more advanced features such as maybe like faces or organs. So there's many architectures that have been created. Some examples are ResNet, Inception, RCNN, regional CNN. And there's a lot of variations on the CNN network for a lot of different needs. And yeah, so CNNs is basically the bread and butter for medical imaging, as well as a lot of structured data, well, structural data. And it can also be used for like sentences and natural language processing for medical reports. But a key thing is that CNNs, like any other neural network, needs a lot of data, right? And like I said before, like sometimes with these rare disorders, the data is simply not there. It doesn't exist. Not enough patients have that, or not enough images of patients who have that disorder are out there, right? So how would we fix that problem? We could either do it with data processing techniques such as data augmentation to increase our data set, or we can do other things like transfer learning. So transfer learning uses a pre-built base model, and so these are models that are trained on very large data sets, such as ImageNet, which has, I think, 14 million images, and it's like it was built by like Fei Ling from like a couple of years ago. And this basically trains a very accurate model, which you can basically use and slice off the end of it, because with transfer learning, the whole principle is that for the first few features of the model, it's going to detect similar features, right? It's going to detect very basic features like edges, right? And because most models are very similar in these shallow features, you can just use their model, which is trained on much more images. However, while transfer learning is pretty great, there's a lot of setbacks for it. So the more alike your project is with the transfer learning model, the more likely it is to work, right? Because if a model was built on cats, dogs, and horses, it's probably not going to be able to detect like cancer or like pneumonia. So the tasks need to be similar. However, one consideration is that on the internet, there's quite a few pre-trained models for medical projects. So let's say you wanted to look at fundus photos, which is pictures of the eye. Instead of using the ImageNet transfer learning model, you could look through GitHub or look through research papers to find a similar model to detect a similar disease, a disease for fundus, a similar disease, and use their model as the base or the backbone for your model, right? So it's important to be careful for transfer learning that it's not always applicable just because, if the projects are too dissimilar, it is likely to not work. Yeah, so the next one is semi-supervised learning. So this one is also pretty good for when you don't have enough data or you have missing labels. So for semi-supervised learning, it uses partially missing labels. So it's a mix of supervised and unsupervised learning. One example is weakly supervised, where you have, it's an iterative approach where we train it on a few labels and then we generalize to the whole unlabeled data and then we repeat that. This is especially good for segmentation tasks because ground truths for segmentation require multiple experts. It's not always there, and you want to make a little go a long way. Yeah, so that's kind of that is. So another thing is feature extraction. So and radiomics. So feature extraction kind of is a more intuitive way of determining progressing your project. So for example, if you were trying to look at a, I'll use the fundus image example again. If you were trying to diagnose glaucoma, diabetic retinopathy, and you hypothesize that the amount of blood vessels in the fundus image, or the thickness of them, or maybe the optic disc size mattered, you would make an algorithm to measure those, right? To measure how many blood vessels there are, how wide is the optic disc, and this would be much more interpretable, right? So you know exactly what's going on, you know what's feeding into the model, whereas generally neural networks are kind of a black box, which you may have heard of before, where you don't really know, you put in the input and you don't really know what's going on inside. You don't know what's being looked at. You don't know what features are important, and you get an output, right? So doing feature extraction and creating these like interpretable features is quite important. So I'd like to talk about radiomics next. So this is kind of an area of radiology where we use statistical features, which are kind of invisible, to make predictions or to make feature extraction for predictions. So examples are first order statistics, grade level run length matrix, and discrete wavelet transform features. So these are somewhat intuitive or interpretable, and they're mostly statistically based. And yeah, so next is we can also use feature extraction with deep learning. So like I mentioned before, there are feature maps with CNNs. What happens when you run the kernel through the image, we get these feature maps that tell us different things. And instead of going through with the model, we can take these feature maps directly and put them into another model or combine them with other features to make an ensemble. And you can use these with more traditional machine learning methods that are not deep learning, like maybe XGBoost, CatBoost, things like that. And yeah, so these are some examples of like what feature extraction looks like. Just a reminder, all the images and all the papers that I'll be talking about will be, in the speaker notes for the slides. So if you're interested, you can check them out. This image is from one of my projects personally, so there's no link for that one. Yeah, so next I'd like to kind of continue the train of thought with black box models and interpretability. So I'll talk about CAMs right now. So what are CAMs? CAMs are class activation maps. So it basically, we take the weights from the feature maps before the global pooling stage where they're all turned into the predictive outcome. Like, yes, this has pneumonia versus no, this has no, this has pneumonia. And it basically tells us what the model is looking at, right? The regions with higher weights look red, while the regions that are blue are not really looked at. And this helps some with the black box problem because we know, what is the model looking at to make this prediction. However, while CAMs are quite useful, it's important to know that they're not always interpretable, right? So models are quite greedy. And what I mean by that is that machine learning models will basically, stop when it sees a region that is highly predictive. So in the image above here, it'll probably just see that and just report that with and while the other regions are blue, it doesn't necessarily mean that those regions aren't important for the prediction. Yeah, so it's something to keep in mind while looking at class activation maps. And there's a couple other ones, I believe. There's the gradient cam, but I probably won't get into too much of that. Yeah, another problem cams have is saliency, which I don't have on the slide, which is that sometimes they just detect some features like edges and stuff like that that are quite prominent and not actually like what exactly is important for the diagnosis or the prediction. Okay. So next we'll look at the one pixel attack and generalizability. So this is actually, I know I talked a lot about how machine learning is like really cool and it can be used for medical imaging, diagnosis and prediction and segmentation, and it's quite powerful. But it's important to know that there are still quite a few problems with machine learning in medical imaging, and it's not best to not jump into it. And here's one of the major problems. So most models actually have very poor generalizability, especially in the academics. So for most papers that you see, like a good portion of them are not going to be generalizable. So one example is the one pixel attack. So if you see on the right, this ship, if you just add a little white pixel here, it predicts as a car very accurately. Same with the horse, predicts it as a frog. So the same thing for medical imaging, right? If you add like maybe an artifact, like a motion artifact or something like that, it might completely change the diagnosis or prediction. So we need to be aware of that these models aren't perfect. And yeah, so another example is cats. So in this paper, they basically looked at someone else's COVID prediction from medical imaging, and they found that if you put an image of a cat here, it predicts it as having 100% COVID, right? With 100% confidence, and that's not COVID. That's a cat. So it's important to know that these models are not perfect, and we need to be able to know exactly. We need to know that we'll tread lightly with when we say that this model has like 99% confidence. It's like really strong. It's not. It doesn't really mean it's like always right. Like these issues with predicting a cat as having COVID. Another thing is that unseen data, especially with academic papers, it might fare really well under test data, but on unseen data, it performs like extremely poor. Like for this one, they said they had 99.7% confidence, and then in the unseen one, it drops down to 75, like 67. So it's definitely a problem, and some papers might have cherry picked data, especially since replication is a huge issue in like deep learning because there's so much data, there's so much like variation in the backpropagation process that if there's a paper out there and you want to replicate it, you could get like wildly different results, right? So how do we improve generalizability? There's a lot of things you could do. A big one is just having better data. It always starts at a data step. The data step is incredibly important. And having like a diverse sample of that is representative of the population. So if you wanted to basically let's say diagnose like skin cancer in in patients, in like all patients around the world, you wouldn't want to only take, Caucasian patients, right? Because that wouldn't be representative, and the model might, fixate on some things that wouldn't be good for if we extend this to other areas. Yeah, so it's something to be careful about, and yeah, so if you try out a model that you found on GitHub and it doesn't work, just know that that's usually how it goes. There's natural variation with deep learning. Yeah, so I guess that kind of ties into why is AI not, well, I wouldn't say not used, but not used as much as we thought in clinics. And yeah, generalizability is a big issue for models trained on, some samples. It doesn't fare well for underrepresented populations. There's ethical problems with, if you're a patient, would you rather be diagnosed by a doctor or a machine, right? There's also lack of high quality images. Like I said before, there's problem with, budget or technology needed, or like the digital infrastructure to basically implement or support it. There's, a lack of technical knowledge sometimes, and AI is still used in clinics. It's just more as a supportive tool, like early warning signal rather than an autonomous a model where so for example, it would alert a physician that this patient probably has pneumonia, and they will get a second opinion. It's more of a tool for physicians rather than replacing them and saying like, oh, I only need what the model says, nothing else. And that has provided a lot of stigma that AI is taking over, and it's but it's not completely true. So now we'll probably get into some of the examples. So the first example is the development and validation of a deep learning algorithm for detection of diabetic retinopathy in retinal fundus photographs. So yeah, this was made in 2016 by a team at Google. And like I said before, they identified a gap that there was a lack of ophthalmologists, I think, in some places that could treat diabetic retinopathy, right, which could cause blindness. So what they did is that they took around 10,000 images, and they basically used a Inception v3 architecture, which is a CNN with inception layers. And they did multiple binary classification. So they basically, looked at does this patient have diabetic retinopathy or not, and then how severe is it, and then is it medium severe or like highly severe, stuff like that. And they found that it outperformed the average ophthalmologist. So this was quite a big breakthrough. This was in 2016, so some of the techniques that were like super novel back then are like slightly outdated now, but it is quite a impressive paper, and they also made a application for it, I believe. Yeah, so the next thing is the RSNA Pediatric Bone Age Machine Learning Challenge. So this was in 2018, and they had a challenge to estimate child age based on bone structure from images. And this was quite important, or had clinical relevance, because it was a tool that could save a lot of time for pediatricians. As the normal process of doing this requires a lot of like checking with diagrams and making sure. So having a quick machine learning tool would be quite helpful. And they used around 14,000 images, and the first place had an ensemble approach, which was to basically take the output from a lot of these CNN models and basically just group them together and create a prediction. The next one is skin lesion segmentation from dermoscopic images. So this is skin cancer or skin lesion. And the reason why this is important is that for some aggressive skin cancers, being able to diagnose it quickly greatly influences the prognosis or like the outcomes for the patient. So yeah, they used something called a ResUnet. So it's kind of a UNet for segmentation, which is and then it's a UNet with residual layers. And then, yeah, it was a segmentation, then prediction task. Yeah, so next, my final slide will be where can you get started? So if you're interested in AI for medical images, there's going to be free data sets for you to play with. Again, data is like a big part of these projects, and you need to be confident in like how you can work with data, where you can get it, and how to pre-process it. So Kaggle is a really big source. There's a lot of, I believe there's a lot of COVID data on there too, a lot of other things. Tryon, I believe that's a data set for fundus images, and Mimic3 is like one of the bigger, free patient databases out there that you can work with. If you have a research question, there's probably data out there that you can look at and play with and maybe test out your hypothesis. Next, there's an increasing amount of machine learning tools out there. So there's things like Keras, TensorFlow, PyTorch for all your deep learning stuff. And there's also PyRadiomics for radiomics, feature extraction. And something that I stumbled upon recently was AutoAugment, which was something developed by Google to find the optimal data augmentation parameters. So yeah, there's a lot of resources on the internet that you can find if you're interested in this kind of stuff. Yeah, so that should be it.
Thank you, Kevin.